Let's take a look at an example problem here where we're going to use impulse and momentum to solve this problem. So we have the system shown here. We have a 15 kilogram slider on a bar. We'll assume the bar is smooth, that way we don't have to worry about friction. And then we have a 10 kilogram mass just hanging from a line. We're going to release this system from rest, and so we know that V sub A is equal to 0. I'm going to actually label that V sub A 1, that's in the initial situation. V sub B1 is also equal to 0. And we're interested, notice, in the time it takes for the velocity of A to reach 0.6 meters per second. So V sub A2 will be 0.6 meters per second. And what we want to know is time. So V sub A2 is equal to 0.6 meters per second. This is all the known information, plus, of course, the masses. And what we want is time. Now, that desire for time is really a critical issue, because what we're going to see in a lot of these impulse and momentum problems, we're going to be looking for time. If we're looking for distances or displacements, we're going to go back to work and energy, because that was involved in work and energy, whereas time is involved in impulse and momentum. Now, later on we'll do collisions and time is not a factor anymore. But if you're being asked for time, in general, we can state that you want to do an impulse momentum problem. If you're being asked for distance, in general, you probably want to do a work and energy problem. All right, so let's take a look at the forces acting on the 15 kilogram mass. So we're going to have M sub Ag, that's the gravitational force due to the Earth acting on mass A. So the gravitational force due to the Earth acting on mass A. Then we also have tension and tension. Even though it's acting on the pulley, we're going to consider that pulley to be part of mass A. So the tension due to the cord acting on mass A. So I can look at the sum of the forces then in the y direction and write 2t minus m sub Ag. Those are the net forces. Now this is equal to the mass of A times the acceleration of A, but I'm really not going to worry too much about that right-hand side. I'm going to concentrate on this side. Then as I look at B, I have a tension up, same tension because it's a massless rope and massless frictionless pulleys. And then downward is a gravitational force due to the Earth acting on mass B in this case. So that's mass B times G. So the sum of the forces in the y direction here, T minus m sub B, G. Again, I'm not going to worry about the right-hand side. So now let's take a look at the constraint. If I look at the length of the cord, I can see that it's going to be this distance, which is the position of A, plus this distance, which is the position of A, plus this distance, which is the position of B. That's the length of the cord, so if I take a time derivative of that, derivative of the length with respect to time, that of course is 0, the cord is not changing length, and that's going to equal 2 times the velocity of A plus the velocity of B. So I can come up with a relationship then that the velocity of A times 2 equals minus the velocity of B, which of course makes sense. If A is going up, B is going down. Now since this is momentum, these velocities are going to become important, so I really want to bring those into account here. All right, so let's take a look at the impulse and momentum just of block A. So A starts off with a 0 velocity, but later on it's going to have a velocity up. And so the momentum up will be mass times the velocity of A. And the forces, recall, are two tensions and gravity. So I can say that the mass of A times the velocity of A1 plus the integral of f dt equals the mass of A times the velocity of A2. Now this is 0 because it starts from rest. And the force is going to be 2t minus the mass of A times g. Now keep in mind, these are constants, so they're going to come out of the integral. And so I'm just going to put in a delta t here after I've done the integration. That's going to equal the mass of A times the velocity of A later. But keep in mind, I'm looking at velocity of A as being 0.6 meters. That's the velocity of A2. Then I also have an impulse and momentum for block B. And that's going to be T minus the mass of B times G They're both moving for the same amount of time, so delta t is the same in each case. That's going to equal the mass of B times the velocity of B. But the velocity of B in the second scenario, again, then that first scenario here, this would be the mass of B, velocity of B1. This is going to go to 0 because it starts from rest. But the velocity of B2, I can get that from this equation. The velocity of B is twice the velocity of A and in the opposite direction. So since A is traveling at 0.6 meters per second, B must be traveling at 1.2 meters per second, and that has to be down. Negative because it's in the opposite direction, twice the magnitude. So what you'll see here is a system of two equations and two unknowns. Unknown in this equation is the tension T and the time interval delta T. Now I'm interested in the time interval. Given that that's what I'm interested in, there's really no sense in solving for the tension. Let's just go right to solving for the time interval. But to do that, I have two equations and two unknowns. What I'm going to do is I'm going to pick an equation, and I'll just happen to choose this bottom one here. I'm going to solve this equation for tension T, and then I'm going to substitute that value in up there. To solve this, I'm going to divide both sides by delta T. So big T, tension, minus weight of G equals the mass of B minus 1.2 meters per second all over delta time. And then I'm going to bring the mass of B times G to the other side. So plus the mass of B times gravity. I'll eliminate this on the left. So this is my tension. So this equation gives me tension. And now I'm going to substitute that value into this top equation. And so I get 2 times tension, m sub b times minus 1.2 meters per second, all over delta t, plus m sub b g, minus m sub a g, all of this times delta t, and that's going to equal the mass of A times the velocity of A, which was 0.6 meters per second. I'm going to bring the delta t inside the square brackets and inside the parentheses, and I'm going to get 2 times the mass of B minus 1.2 meters per second. And when this delta t comes in, it'll cancel that one in the denominator, plus 2 times the mass of B, G, delta t, minus the mass of A, G, delta t, equals the mass of A times 0.6 meters per second. This has no delta t in it, so I'm going to bring it to the other side. So I'm going to get 2 times the mass of B, G, delta t, minus the mass of A, G, delta t, equals the mass of A times 0.6 meters per second. Plus, because this minus sign will become positive when I bring it to the other side, 2 times the mass of B times 1.2 meters per second. I can pull the delta t out, and I'm going to get delta t equals the mass of A, 0.6 meters per second, plus 2 times the mass of B, 1.2 meters per second, all over 2 times the mass of B, G, minus the mass of A, G. And I'll substitute in my values now. M sub A is 15 kilograms times 0.6 meters per second, plus 20 kilograms, that's twice the mass of B, 1.2 meters per second, all over 20 kilograms minus 15 kilograms times 9.81 meters per second squared. And if I solved all that out, I get 0.673. I look at units, I have kilograms, meters per second in the numerator, kilograms, meters per second squared in the denominator. Kilograms cancel. I end up with meters per second divided by meters per second squared, which is meters per second times seconds squared over meters. Meters cancel, seconds cancel there, I'm left with seconds, which is what it should be. I'm looking for a time. So this is the time it takes block A to reach a speed of 0.6 meters per second. Okay, let's discuss the concept of conservation of linear momentum. We'll talk about angular momentum in a later lecture. The idea behind conservation of linear momentum is that the sum of the external forces is zero. And a lot of this goes back to Newton's second law. Remember, Newton's second law says F equals the derivative of mass times velocity with respect to time. But if the external force is zero, then dmv dt equals zero, or the derivative of mass times velocity with respect to time is equal to zero means that mass times velocity must equal some constant, because the derivative of a constant is equal to zero. So what that means is mass times velocity in the initial situation equals mass times velocity in a later situation. Now, if you go back to that previous example that we just finished, gravity is acting on this system. And so it does not have zero external force. The tension would be internal to the system, but gravity is acting on the entire system externally. And so momentum is not conserved. And we saw that. We started off with zero momentum, and we ended up with some non-zero momentum later on. So this is only going to be true if external forces are equal to zero. Now you'll notice the summation. What the summation sign is telling us is maybe there's more than one particle. So an idea would be, assume for a moment that you and several friends are in a spaceship, so you're in deep space, far from any gravitational forces, and you attach to each other via rubber bands. If one of you pulls on the rubber bands, any one of the rubber bands or more, you're going to start moving towards each other. And then once you get close to each other, you can shove off of each other. But keep in mind, when particle A and B are connected by a rubber band, and particle A gives a tug on the rubber band, B is pulled to the left, but A will be pulled to the right. And Newton's third law says equal and opposite forces. So these two forces are equal in magnitude, opposite in direction. Therefore, the net force on the system as a whole is zero. The net force on A is not zero. The net force on B is not zero. But the net force on the AB system is zero. Then once A and B are next to each other and they push off, A is on the left, B is on the right, B shoves A to the right, B shoves A to the left. Even if A isn't doing anything actively, B shoves A to the left, A is going to push B to the right. And so equal and opposite forces, yet again, the two objects are going to move apart. The net force on A is not zero. The net force on B is not zero. But the net force on the combined system A and B, that will be zero. And so the momentum of A and B combined before the collision will equal the momentum of A and B combined after the collision. The individual momentums of particle A and particle B will change, but the net momentum of particle A and B together will remain the same. If they had some momentum to begin with, they will continue to have that momentum as a whole. Again, the individual momentums might be different. You could think of two ice skaters going down the rink, and one pushes off on the other, but not in the direction of motion. So maybe there's two ice skaters moving to the right, and the upper ice skater pushes the lower ice skater. The upper ice skater will move in that direction, the lower ice skater will move off in that direction.